Hello, children. So yeah, I'm in Smart Notebook. I don't like writing in Smart Notebook as much as that other application, but nevertheless, it's useful for what we're doing here. We are going to today talk about, I want a different color. We're going to look at applications of vector multiplication. Okay, so we've got applications of vector multiplication. Hope everyone is doing well still. Yeah, okay, lovely. So vector multiplication. We know there are two types. There's going to be dot product and there's going to be cross product. And so we're going to look at some applications of them. So one of the applications that we can use them for is we can find the area of a parallelogram defined by two vectors. Okay, so that's exciting. So imagine we had this, and we'll make this one this color. There's one vector, and then we're going to grab a different color, that color red. And here's another vector. And I want to find the area of the parallelogram defined by those two vectors. And so it's kind of like, it's pretty easy to envision, right, that these two vectors, nicely form for us a parallelogram. There it is right there, right? So there is the area of the parallelogram. So what's kind of cool, and we talked about this, is that we said by definition, in fact, earlier, one of the things that we know is the magnitude of A, if I call this vector A and this vector B, the magnitude of vector A crossed with vector B is, in fact, the area of that, right? And so that is, if we have algebraic vectors, so, if we have algebraic vectors for these things, we're good to go. So algebraic definition right there, boom, there it is. Just go ahead and calculate what the cross product is. And if we had geometric vectors, well, we defined what it was. We said, oh, it's the magnitude of A times the magnitude of B. And because remember, this is the definition of cross product, and cross product is times the sine of theta, where this is the theta down in there. Okay, so that's what we've got. So there is how we can calculate the area of a parallelogram. We can just take and we can do the magnitude of the cross product. If we have the A and the B vector as algebraic vectors, and if we had them as geometric vectors, that's what we do right there. Lovely. Let's go on. How about this color? So second one, how about the area of the triangle defined by two vectors? Okay, and I'm going to simplify my life here. This is why Smart Notebook is handy. I'm going to clone that stuff, pull that on down here. And then if we thought about the triangle, that's too thick, don't be silly. So this is a triangle. It's defined by those, right? There it is there. Well, it probably doesn't take you long to come up with a theory of how we could do that. Well, certainly it's only half as big as the parallelogram. So we could do, it is the magnitude of vector A crossed with, it's the magnitude of A crossed with B, and then simply divided by 2. Boom, Bob's your uncle. There you go. So here's a couple definitions. We haven't done a lot of exercises as we normally would in class, simply because I don't want to burn a lot of your time on those things. I'm more concerned about making sure that we get access and exposure to these concepts. But let's try a couple of examples. Yeah, this doesn't write anywhere near as nicely as that other piece of software does. Okay, so imagine that we had the vector A, which was going to be 1, 7, and 13. And then vector B is going to be, well, how about 4, -8, and 3? And what I want you to do is a few things. I want the area of the parallelogram. Okay, so I want the area of the parallelogram defined by these. So first question is area of parallelogram. And the second question is going to be area of the triangle. And then I also want to know, question 3 is going to be, what is the angle between A and B? There is a, what the heck? A woodcock buzzing in the background. If you want to hear a funny noise, look up the woodcock call on the YouTubes. And I bet you've probably heard it before, but it's a weird sound and you wouldn't think a bird made it, but it is a bird. Okay, so, and then the last thing I want you to do, just for good practice, is for you to sketch the parallelogram. Okay, so first thing, I want to know what the area of the parallelogram is. So number one, well, I know that's the magnitude of A crossed with B. Well, that of course necessitates I need to calculate what A crossed with B is. So let's go ahead and we're going to do that. So we're going to do 1, 7, 13, 1, 7, 13, and then I'm going to do 4, negative 8, 3, 4, negative 8, 3. You don't get to play, and you don't get to play. So we're going to do downy minus uppy. So we're going to do 21 minus negative answer. So 21 plus, that's going to be 80 and 24, so plus 104. So I guess that's going to be 125 if I've done that correctly. And then next one, we're going to do, a different color just because I can, downy minus uppy. So we're going to do, that's 40, 52 minus 3. So 52 minus 3. So I believe that's 49, although I stand to have made a mistake on that. And then finally, we're also going to do downy minus uppy. So that's going to be negative 8 minus 28. So that is negative 36. So the cross product of A crossed with B, right? So A cross B is going to be equal to 125, 49, doesn't really look like 49, negative 36. Wow, garbage writing on my part, big time. Okay, lovely. So there's it is. So if I want now the magnitude, which I do, it's equal to the square root of 125 squared plus 49 squared plus 36 squared. Yeah, it's really negative 36 squared, but I know it's going to be positive, so I don't really care. So that's going to be equal to, if I've done this correctly, and I have a note on it because I've done it before, so I think it's correct, 19,322, the root of that. So that is what the area of the parallelogram is, right? It's that, whatever that is. So I have no idea. But that's what it is. And then that's for question 1. And so for question 2, wow, it's really not very smooth. Question number 2, it's just going to be that root of 1900 and 19,322, and I'm just going to divide that by 2, and there we go. So easy peasy. So now I want to know the angle between A and B. Well, here's the short form for doing that. Of course, I remember that A dotted with B is equal to the magnitude of A times the magnitude of B times the cosine of the angle in between them. So I can do some rearranging and I can say, oh, that means that it's going to be that it is the cosine of theta is equal to A dotted with B divided by the magnitude of A divided by the magnitude of B. So that's probably where my instinct would jump me into. And if you've got that memorized, lovely, easy peasy. However, in this circumstance, we know that the A crossed with B is equal to or the magnitude of A crossed with B is equal to the magnitude of A times the magnitude of B times the sine of theta. Okay, we already have that, the magnitude of A crossed with B, which is lovely. So then this actually ends up being, if I rearrange this, the sine of theta is equal to the magnitude of A crossed with B over the magnitude of A times the magnitude of B. In this case, this one ends up being easier because I've already calculated what the magnitude of A crossed with B was. This will also always work to find an angle for you. However, cross product is substantially more involved than dot product. So this is why we would normally use this piece here and less favorable to use this. But in this circumstance, certainly because we've already got what the magnitude of A crossed with B is, it's going to be actually easier to do that. So we would say then, oh, that means the sine of theta is equal to the magnitude, well, that is the root of 19,322 divided by the magnitude of A. So if we go back up here, we're going to need the magnitude of A. So let's do this over here, I guess. So the magnitude of vector A is going to be equal to the root of 1 squared plus 7 squared plus 13 squared. So that's 1 plus 49 is 50. I think that's 169. So that's like 219, I believe. Yeah, so that's equal to the root of 219. And really quickly grab the magnitude of vector b, because we need that as well. Magnitude of vector b is equal to the root of 4 squared plus 8 squared plus 3 squared. So that's equal to 16 plus 64 is 80. So the root of 89, I think. Root of 89. But you get the idea. Yeah, I think that's what it is, because that's what my note says. So yeah, that's good. So it's going to be over then the root of 219 times the root of 89. And then we would just do the sine inverse of that, right? So theta is equal to the sine inverse of the root of 19,322 divided, oh no, or sorry, that divide's not in the right spot. Oh dang, 19,322 divided by the root of 219, the root of 89, okay? And whatever that ends up being. Lovely. So that's how we could have found the angle. We also could have totally done it with the dot product definition. But if you've already got the cross product done, you're good to go. Okay, lovely. On we go. Now, the last thing that we want to do is we want to sketch that parallelogram. Okay, easy peasy. So let's draw in our axes. Get me a straight black line. Hold the shift key so that it goes straight. Well, thing of beauty. There we go. And I know, does it work like this? Yes, it does. I'll adjust that in a second. So here we go. There we are. Lovely. Okay, so I don't remember what the vectors were. So let's make a copy of those, because I can do that in Smart Notebook. Yay, copy. And that right click doesn't work with the pen. Paste. Okay, there we go. All right, so A is going to be, let's do A in blue. Oh, well, whatever. A is going to be in blue. Why am I not in blue? A is going to be in blue. Okay, there we go. That's not, whatever. A is going to be that color. So out 1 over 7 up 13. So it's way the heck and gone up here. So let's grab us the vector and then say, there it is right there. That's going to be vector A. There's vector A. And then we need a vector B. So let's grab a different color for vector B. This color. A different color. That looks pretty much the same to me. This color. That color. Yeah, it's a different color. So vector B, so we're going to go out 4, about to there, back 8, out to there, and then up 3. Oh, it's pretty darn close. It's probably going to just straighten that out. And so let's do this and then get that color. Was it that? I think it was that. So from there, yeah, I knew that was going to happen. Let's say it's there. Let's move that one up. So the parallelogram then, defined with that, is going to be this. Go like this, and like this, right? So there's our parallelogram. Easy peasy, lemon squeezy. There's our parallelogram. Maybe shade that in just so that we can see what's going on. That color. Yeah, there it is. There's our parallelogram. Lovely. All right, good. All right, on we go. Next one. I'm gonna tell you, back in the day, this was Mrs. Whitty's probably favorite lesson of the year, and she used to bring in a Christmas ornament, and I'm gonna show you or tell you why in a moment. So the next one that we're gonna talk about here is this is like number 3, I think, the volume of a, and I've said this word before, no, there's only one R. Volume of a parallelepiped. Okay, so a parallelepiped. Here's the definition. So if you think about a square and then a rhombus is a tipped over square. And if we have a rectangle and then we've got a parallelogram, typically speaking, a parallelogram is a tipped over rectangle. A parallelepiped is a tipped over in 2 axes rectangular prism. Ooh, baby. Okay, so yeah, so what we're going to do is I'm going to define a parallelepiped. So if we think, so I mean, a rectangular prism is also a parallelepiped, but it doesn't have to be nice like a rectangle. It doesn't have to have all right angles in the corners. In fact, the only definition is that the opposite faces are parallel and that they are the same shape and size. So let's just really quickly sketch one of these things so you've got an idea of what's going on. So if we had this, and I'll try and make it as reasonable and easy to kind of see what's going on as I can. Clone. Oh, didn't do a good job with that one. Stretch you out. So there is one face of our parallelepiped. And then imagine, so this could have been a vector here. So let me just kind of vectorize this guy. So imagine that this was vector A. And this guy down here was vector B. And the 2 vectors alone, they can create a parallelogram, obviously. I'm going to add some color to this because it's going to be important just to be able to differentiate these things. I'll make that guy blue because I like the blue. Make this guy, no, up here, this guy red. Looks the same color to me, but I'm sure you can tell. So that means that this guy also should have been red, and this guy should have been blue. I don't need to copy it. I just need to make it blue. There we go. And then we toss in a 3rd vector. Okay, so here comes our 3rd vector. And I'm just going to use this, and we'll go green. I think is that green? Is that green? Is that green? I don't know. We'll use that one. So 3rd column, 2nd row. We toss in, too big. I don't want it that big. We toss in another vector. So here it is. And so it's kind of hard. You're like, I don't really see it. So watch what we're going to do. Stop that. I'm going to have to go with the mouse. All right, so grab this and turn on infinite cloner, and turn on infinite cloner, and turn on infinite cloner. So I didn't want to just clone it. I wanted infinite clones. Infinite cloner. There we go. So what we're going to do is I'm going to create the different faces that go with this guy. So imagine then that I'm just going to drag. Can I do that? Come here. a copy of that one over and put it at this vertex. Oh, it's not at the vertex. There it is. And then I'm going to drag a copy of this one up. So what I'm going to do is I'm going to, why are you not doing that? There we go. So now I have two faces, right? So I've got the face that A and B made, and maybe I should write in there that we're going to have a vector C. So let's change B to be red, because I think B was red, wasn't it? Yeah, it was red. And A, we're going to change that guy to blue, because A is blue. And then this vector up going on in here is going to be vector C. And it was that one right there. Yeah, vector C. Okay. So I've got the face that's made with A and B, and I've got the face that's made with C and B. Now I need the face that's made with A and C, and it's kind of harder to see what's going on here, but nevertheless we're gonna get there. So come here, you. So I'm gonna go up and attach that to this vertex, and I'm going to attach this one to this vertex. And so that's, you can kind of get that this is, imagine we took a rectangular prism and we kind of tipped it over. This is what we're going to get. So let's make another, oh, no, you stay out of the way. Get that one and come here. Move all this stuff out of the way. Like that. And then I need the blue as well. There it is. Oh, stop that. Need the blue. And then another red. That's not red. Another, stop. Another red. And then what we actually have is we have a rectangular prism that has tipped. Okay, and so that is a parallelepiped. And what we want to know is how to find the volume of a parallelepiped. The kind of the definition or the derivation, I guess, of how to get this is actually pretty cool. But let's just say that the volume of a parallelepiped is equal to the area of the base, right? So the area of the base. So if we envisioned that this face right here was the base of the parallelepiped, right? So the parallelogram made with A crossed with B. So the volume of the parallelepiped is equal to the area of the base times the height of the parallelepiped. So now we have to be careful. So it's not just the magnitude of this, right? This is tipped over. So, if this was a box that had kind of leaned over, this dimension is the ladder leaned up against the wall. It's longer than what the height of this box is, right? And so if I were to insert into here, what's a good color to use? How about that one? Right. So if I were to insert this and it came up, and so it is at, is that black? I think it's black. Right angles with this face, and it's going to be hard for me to kind of convey this, but it's at right angles with the face that's up here as well. This is the height. Okay, that is the height. So let's go back to what we got going on over here. Is that blue? I think so. We know the area of the base is equal to the magnitude of A crossed with B, right? Because we've said that's how to find the area of the height. No, the area of a parallelogram. Okay, I was looking at something else. Now I need the height, and I guess I'm kind of going to go into the definition. If the height has to be perpendicular to A and B. How do we get something that's perpendicular to A and to B? Well, by definition, A crossed with B is perpendicular to both A and B. So a normal vector, and normal meaning at right angle, to this plane, we need a normal vector to this plane. By definition, A crossed with B is a normal vector to this plane. So A crossed with B is perpendicular to both A and B. In fact, it is normal. And normal doesn't mean like average, everyday, ordinary in this context. It means right angles too. So A crossed with B is normal to this. Why is that useful to us? Well, if we took vector C and we projected it onto the A crossed with B, what we would actually get is we would get the height of this guy. Okay, so let's get the height. So height is going to be equal to, so height is equal to vector C projected onto A crossed with B, right? And so that's going to just, the shadow on here of C is going to be the height of this. So projected onto. So that means that we're going to do C dotted with A crossed with B divided by the thing that it's onto. So this is really like A dotted with B divided by the magnitude of B. It's C dotted with A cross B divided by the magnitude of A crossed with B. So we can go back up here and say, ha, there is the height. The height is C dotted with A crossed with B. And I'm going to put those guys in brackets, divided by the magnitude of A crossed with B. Now, just a good thought exercise. Why did I immediately jump into saying I have to put brackets around these guys? Think about it for a second, and I'm going to tell you why. Hopefully you've figured it out, but just in case you haven't. If I didn't do that, then I would do multiplication in the order that it appears, and I would do C dotted with A. And I can do C dotted with A all day long, but what's the result of that? The result of C dotted with A is a scalar. And then if I tried to cross a scalar with a vector, the world explodes, and it's not going to happen. So that's why that has to be in brackets. Now, look what we've got. This goes away with this. And we are left with C dotted with A cross B. Okay, and that is the volume of a parallelepiped. But what's interesting is dot product is commutative. So we could say that it's really A crossed with B dotted with C. Now, it's good practice to put those in brackets, but realistically, I don't even really need those in brackets because if I just did it in the order they appeared, we'd be good to go. So that's pretty darn cool. That is the volume formula. Now, you might think, well, what happens if I didn't know that A, like if I was just given 3 random vectors, how do I know which one forms the base? The cool thing is, I need a vector symbol, you could do this in, I'm going to be careful here, in any order that you want. The crossing has to happen first, and then the dotting. But you could also have said, well, I'm going to do A crossed with, that's the same thing, A crossed with C. Oh, let's get rid of that. That's still not getting rid of. So I'm going to do, back where we were, A crossed with C and dot that with B. And that'd work. Or you could do, I'm going to do B crossed, that's on a B, C crossed with B, dotted with A. That works as well. Okay. So the interesting thing is that this is sometimes called a triple product or a scalar vector product, whatever. If you have the 3 vectors that form a parallelepiped, take 2 of them and cross them, and then take the result of that cross and dot product with the 3rd vector, and you now have the volume of a parallelepiped. But there's one caveat here. And everything I've said is all true, I think. So those are all good. But what's cool is that sometimes the result of this is negative. And of course, we don't want a negative result for volume. That's nonsensical. So we are going to always take the absolute value of the result, right? Because we definitely want a positive volume. A negative volume is silly. Okay, so if it comes out to be negative, don't fret. It doesn't necessarily mean you've done it wrong at all. It could very well be that you've done everything correctly. So the answer must be positive. So it doesn't always come out to be positive. You make it positive, right? So we force the result to be positive. Okay, lovely. So let's do an example of this. So an example. So find the volume of the parallelepiped formed by vector A is going to be equal to 1, 2, 3. 1, 2, 3. Vector B is going to be equal to 4, 7, 3. And vector C is going to be equal to -1, -1, and 0. Okay, so I want the volume. So volume I know is like A crossed with B dotted with C, sometimes called the triple product. There's lots of different names this goes by. So I'm going to do A crossed with B. Okay, so 1, 2, 3, 1, 2, 3, 4, 7, 3, 4, 7, 3. Go away, go away. Downy, uppy. So we're going to have 6 minus 21, which I think is -15. And then we're going to have downy 12 minus 3. So 12 minus 3 is going to be 9, I believe. And then we're going to have downy 7 minus uppy 8. So 7 minus 8 is -1. So A crossed with B is going to be equal to -15, 9, -1. That's the first part. And then, so I'll write that. So we're going to have -15, 9, and -1. And then I'm going to dot that with -1, -1, 0. Okay, so that's going to be 15 minus 9 plus 0, which is 6. And so there we go. So the volume is 6. Now, as a challenge problem, something for you to think about, imagine instead of asking for the volume, I asked for the surface area of that thing. How would you go about doing it? So stop and think about it for a bit. How would you go about finding the surface area, right? So what would you do to find the surface area? Jumping all over hell's hot baker. Here we go. So surface area. So what about surface area? Remember a couple years ago, I didn't do surface area in a note, and then I put it on a test, and people lost their mind because, oh no, you haven't taught us that. Well, I didn't, but hopefully you'd figure out how to do it. If we go back up, there are, and did I do a diagram? Yeah, I have a diagram here. There are 3 distinct faces. There's the face made by AB, there's the face made by AC, and there's the face made by BC. B and C. So this guy. And so we could find the area of any one of those faces pretty easily. The area of AB is just the magnitude of A crossed with B. And then the area of AC would be A crossed with A crossed with C magnitude, and then C crossed with B magnitude, and you double each of those and add them up, and you're good to go, right? So for surface area, and I'm not going to actually work it out, but surface area is going to be equal to 2 times the magnitude of A crossed with B plus 2 times the magnitude of A crossed with C plus 2 times the magnitude of B crossed with C, right? So mechanically, a pain in the butt, but conceptually, not hugely difficult. And that's fairly true of this unit or this whole course, frankly, in general. It's just replete with areas where you can make mistakes, right? Conceptually, it's not hugely difficult. You can wrap your mind around stuff. Mechanically, really easy to screw up. Okay, so for some homework questions, I think this video has been shorter, although when I hit the stop button, it'll tell me how long it was, and I'll maybe find out I was wrong. So page 415, numbers 4, 5, 6, and 7. And I will remind you, not many people have come to me lately about this. But if you encounter problems with the homework that you're trying, by all means, shoot me a question in an email, or post it on Classroom, whatever you'd like. Again, hope you are well, children. Have a lovely day.